Welcome to Pre-Calculus. Today we will investigate solving exponential equations. We'll take a look at two strategies to solve four examples. Our first strategy is to equate the bases. So this first equation, 2 to the power of 2b equals 16. One strategy to solve an exponential equation is to make the bases the same on each side. So as I look at my two bases, I have base 2 on the left, and it actually has a power to the power of 2b. On the right side, I don't have any power, but I have a base 16. So when I consider my two bases, the smaller of the two is the 2. So I want to think, can I write 16 as 2 to some power? And it turns out if I do a factor tree of 16, that's 2 times 8. 8 is 2 times 4, and 4 is 2 times 2. And I count those up. 16 is 2 to the power of 4. So what I want to do is I want to rewrite the equation with that substitution. Instead of 16, I'm going to write 2 to the 4th power. And on the left side, I'm not going to change 2 to the power of 2b. Once I have that structure where the bases are now equal, what I want to do is create a separate, smaller equation where I equate the exponents. So down below, I'm going to write 2b, the exponent on the left, base 2, equals 4, which is the exponent on the right, base 2. And I want to solve that small associated equation. And I don't need to do much to do so. In this case, I just need to divide both sides by 2. And I get the solution that b equals 4 divided by 2, or 2. Let's take a look at a second example that uses that same strategy. Here I've got more than one base. So on the left side, I have 3 to the power of negative 3n minus 2 times 3 to the power of n minus 3 equals 243. So I got to do a few things before I can make my associated exponent equation. Let's see what our common base might be. So I've got on the left bases of 3. So that's a good clue to start there. That's a prime number. And then 243 here on the right side. I don't know how many 3's, if any, are factors of 243. So what I'll start doing is creating a factor tree of 243. So I do see it is divisible by 3. If you add up the digits, 2 plus 4 is 6, 6 plus 3 is 9, 9 is divisible by 3. Therefore, 243 is also divisible by 3. And I believe if I divide that out, 243 divided by 3, 3 times 8 is 24, and then 3 times 1 is 3. So it turns out 243 is 3 times 81. And now I have some familiarity with 81. That's 3 times 27, which is 3 times 9, and then 9 is 3 times 3. So 243 is 3 all the way. In fact, it's 3 to the power of 5. And that's what I'll convert this right-hand side to. I don't want to call it 243. I'm going to notate it as 3 to the power of 5. On the left side, I need to combine these two bases of 3 to different powers. And remember, to combine two products where I'm got same base, different powers, I have to add the powers. So on the left side here, I'm going to get 3 to the power of negative 3n minus 2 plus n minus 3. So I'm going to add those two exponent statements up. And I could simplify that just combining like terms. Negative 3n plus n is negative 2n. Negative 2 plus negative 3 is negative 5. So I have the arrangement where I have the same bases, one on each side, to different powers. So I'm ready to make the conversion to a associated exponent equation. So this is now negative 2n minus 5 equals 5. And that I want to solve. That's a simple linear equation. So I'll add 5 to each side. And I see that negative 2n then equals 10. And to solve that, all I got to do is divide by negative 2. And I have a solution, n equals negative 5. Those two examples use that similar strategy of equating the bases. Let's take a look at two examples that don't show that feature. Here I've got the equation 10 times 12 to the power of n minus 4 equals 4. So what I want to do in this case, when I clearly have a lot of pieces moving around, is again isolate the base to a power on the one side. Since I only have one base to a power here, I'm going to isolate 12 to the power of n. So I'm going to start off by adding 4. That's a good general strategy in any equation solving, is to cancel out anything added or subtracted. So now I have 10 times 12 to the power of n equals 4 plus 4, 8. And then again, if my goal is to get the base to the power by itself, I want to divide this 10 multiplier off of the left to cancel, and then off of the right. And what that's going to give me is now 12 to the power of n equals, if I reduce 8 over 10, 4 over 5. So if I were to try my strategy of equating the bases, I really would have a hard time finding a common base to a power for 12 and 4 over 5. And in truth, a lot of times we're not able to use that strategy. But we have another strategy, which is the logarithm. So the way I would use logarithms in this instance would be to apply logarithm of the base that I have in the exponential. So I see the only base that I've got here is 12 to the power of n. So to use the logarithm strategy, I want to apply log base 12 to both sides of this equation. Now I choose log base 12 because of how it's going to interact with that base 12. Recall using our properties that if I take the logarithm of a base raised to a power, the power descends out front as a coefficient. So this is now n times log base 12 of 12 equals log base 12 of 4 over 5. Last thing for us to do on this equation is to reconcile log base 12 of 12. So remember, what a logarithm is asking is the base 12 to what power would equal the argument, in this case also 12. And so for us, because we chose logarithm base as the same base as our exponential, that's always going to equal 1. And so essentially this is going to cancel, and we really have our solution, n equals log base 12 of 4/5. We can get a decimal approximation for that value. Again, that's asking 12 to what power would equal 4 over 5. But let's go to the calculator to estimate. So to put a logarithm in, we go to the keypad, over to functions, to the miscellaneous tab, and we select log base a. That allows me to put in my base. So log base 12 of, again, let's check on that value. That was 4/5. And that has the approximate value of negative 0.0898. So we'll take that back to our notes screen to finalize and just ask ourselves if that's a reasonable answer for this. So negative 0.0898. Is it a reasonable answer? 12 to the power of a negative number that's smaller than 1 should give us, in fact, roughly 0.8. That makes sense. Let's take a look at one last example. So this example is -7 times 8 to the power of 2x minus 8 plus 4 equals 4. So again, my goal is always to isolate the base to the power. So two things to move here, the 4 and the -7. So again, I'm going to subtract 4 first. And we see something happen here that's really telltale. I get a 0 on one side. So it's going to be -7 times 8 to the power of 2x minus 8. But the right side is now 4 minus 4 is 0. So as I continue throwing terms over onto that right side, divide by -7, cancels on the left, it doesn't change much on the right side. And I get 8 to the power of 2x minus 8 equals 0. And I need to pause right when I see that occur. When I have a base to a power equaling 0, I have to pause and ask myself, is it possible to have that arrangement? Can I raise the base of 8 to some number and achieve 0? Well, when I think about an exponential function, I always have for a parent function a horizontal asymptote on the x-axis that tells me my y value will never be 0 or negative. And so what I look at and consider as I get this arrangement base to a power equals 0 is that there is no solution. There's no power that I can raise 8 to so that it will equal 0. And at that point, I just make a claim that there is no solution and say case closed. Well, thank you for joining for this investigation of solving logarithmic equations. See you soon.